and Cherenkov with time got a Nobel Prize for this discovery. So it's extremely widely used in studies of elementary particles. And nowadays, this is also a very important technique to study cosmic radiation, big detectors which are based on detection of this Cherenkov radiation. Cherenkov radiation is a kind of a very gentle way to study particles, because in many cases, like for instance in Thomson experiment, you have electron which essentially hits the target and drastically changes its properties, or particle is absorbed. Now, Cherenkov radiation is not very energetic, so particle doesn't lose much energy on this emission. And so you can really follow properties of the particles, not disturbing strongly its properties. Now, what is the mechanism of Cherenkov radiation? From a microscopic point of view, this is an effect when charged particle moves in the electric medium and polarize molecules of this medium. So that, for instance, if we have here negative particle, and we will make a snapshot of the picture, what we will observe that molecules around this particle are polarized. So it's plus, minus, and of course, at remote distances, this polarization becomes weaker. So here you have stronger polarization, then it becomes weaker. And here it's weaker, right? So at remote distances. So particle polarizes. Oh, I have forgotten to switch on. So particle polarizes medium, and then it moves further. What happens is depolarization, right? So you kind of, in a sense, excite molecules, and then it is de-excitation, and they emit some light. So what is important is that this is the electric medium. Otherwise, particle will just produce currents here if there are free electrons, and it will not be such a mechanism. This is from microscopic point of view, so that it's excitation and de-excitation of molecules. We are saying that particle produces Cherenkov radiation, but in fact, what produces radiation is medium polarized by particles. So it's not immediately, but it's medium which polarize the particle. From macroscopic point of view, you can consider this polarized medium as a dipole. So you can kind of make the integral characteristic with predominantly plus charge here and minus charge here. So let me ask you, come in time, please. Manage somehow to come in time, because I will not wait. I will just start the lecture exactly when it is proposed. So from this macroscopic point of view, what is formed is this dipole, which then emits light. And what happens is coherent growth of this dipole so that this polarization occurs in synchronized way. It's not like, one molecule is polarized, another close one is not, then another one. So that polarization occurs in coherent way, so they're kind of synchronized. And you can treat it as particle is moving, and then it produces this dipole, which becomes stronger, and then it kind of annihilates, producing the light. So, if velocity of particle is bigger than phase velocity of light, so this is velocity of particle, this is velocity of light in medium. And let me put here phase velocity. Of light in medium. And this is velocity of particle. Which is moving. Then what happens is that coherent front of radiation is formed. Which is similar to the front of shock wave. If you have the plane which is propagating, which is flying with velocity bigger than sound velocity in the air, then it produces shock waves. So in the same way here, so the radiation is not just isotropically emitted, but it has kind of preferable directions, and these coherent fronts are the fronts of the equal phase. And when you have these equal phases, remember we discussed this coherence, which is general issue, then you have kind of enhancement of the effect. So that phase is formed, provided that particle moves faster than a velocity of light. But this is phase velocity. Right? It's not group velocity. For group velocity, of course, that is not realized. So phase velocity is important. Now let me explain some notions here. And one is a phase velocity. What is this phase velocity, first of all? So let us consider plane wave in medium. And if you have plane wave or light propagating in medium, it is described by such an exponent t minus k n x, where n is a refractive index. So in vacuum you would just have n equals 1, but in the medium, probably you know this from optics, what you will have that incoming wave actually scatters on the scatterers, and then when you sum up effect of secondary waves produced by the initial wave, then that summation can be reduced to just appearance of this refraction index or refractive index. So what is staying here we call the phase, and the phase is Et minus k and x. K is momentum, E is energy. Now phase velocity is the velocity with which a given value of the phase propagates. So that you can imagine this oscillatory dependence, and this wave propagates, and the phase velocity is velocity with which, say, maximum propagates. It's not a group velocity, and group velocity is when you have, since particle is described by not just a single particle of light, not by a single plane wave, but usually have some uncertainty, and you produce kind of some interval of momentum of the particles. So this ensemble of plane waves form the wave packet. And so group velocity is velocity of motion of the packet itself, which is composed of many plane waves. Now, how we compute velocity, phase velocity? So let's take E t minus k and x to be constant, since we are following a definite point of definite phase and see how it propagates. From here we can find that x equals E t divided by k n minus constant. Now, velocity we just differentiate. This is dx over dt. So, v phase equals dx over dt. And from this expression we are getting E over k and n. And for the light, if E and k they are the same, we will get C over n here, which is 1 over n. Okay? So the phase velocity actually can differ from, this is since we are using units c, from velocity of light in vacuum. And if n is bigger than 1, and for instance in water, so if n is bigger than 1, then phase velocity is smaller than c. And in water, n equals 1.33, substantially deviates from 1, and therefore it's easy to get that velocity, phase velocity of light is substantially smaller than velocity of light in vacuum. And therefore, in such a medium, it is easy to have particle which is moving faster than, say, 1 over 33, 1.33 of velocity of light. So that the condition for formation of coherent front easy to satisfy. And in fact, Cherenkov, he was looking for the light in water precisely, and he saw some shining due to this Cherenkov radiation. I will show you some slides, maybe next time. And for instance, if you take reactor, and reactors, so they are surrounded by water, and a lot of electrons are moving in the water. And the water is blue just because of this Cherenkov light, so you can see easily this. Now let me explain how this coherent front is formed if particle moves faster than velocity of phase velocity of light. So you can imagine, by the way, so let me just say, so you have a wave packet, which is actually a superposition of many plane waves. So you can easily imagine the situation that a wave packet moves with one velocity, but this oscillatory pattern inside this wave packet moves with another velocity. So it's kind of is moving slower than, let's say, maximum of the wave packet. Okay, so one can use classical picture to explain how this front is formed, and what we are using is Huygens construction to explain what I will use to explain how this front is formed. So what I'm saying that if particle moves faster than velocity of light, phase velocity of light, then the front of equal phase is formed, Frontal specific shape. So let us use Filton's construction. And the first, suppose we have particle which is produced in some point x equals 0, t equals 0. It propagates and it is absorbed at some point xf and tf. Well, actually, it's not necessarily that it is absorbed, we just can consider a given interval of time. So what particle will do, it will emit light, or this Cherenkov light, and again I'm saying that it emits light, but what it does, it actually polarizes medium, and that medium emits light. It will emit light from each point of the trajectory, right? So, and light will propagate somehow in different directions. Let us find position of front, and actually what is emitted are this spherical waves from each, so from each of individual point, things like that. Okay. So let us find what is the front of light in the momentum of time ft. So if particle is produced in point x0, so it propagates some time, and we consider the point xp emission from which it emits the light. So what will be the front of light emitted from this point xp? And it emits the light. So the time of propagation of particle in this case is given by xp divided the velocity of particle. So at this time, particle will be in this point xp, and then time of propagation of light will be Tf minus T particle again. So I want to compute what is position of light on this sphere of emitted light in the moment of time Ft. Also Tf, sorry. So this is the time of propagation of particle here. So then this time is left for propagation of light. And so I can write this as Tf minus xp over the velocity of particle. And therefore the distance x the light propagates is t minus xp v multiplied by velocity of light. So this is x gamma. So this is the radius of the sphere, or the front of the light, emitted from the point xp. And of course we need to consider different points xp, so the particle will emit from each of these points. So what is important here is that this xp is a linear function of xp. So when xp is 0, so in this case you are considering light emitted from initial point, then X gamma is given by TF multiplied by V gamma. Right? Now, if XP equals XF in the final moment of time, there is no time for light to propagate, and therefore X gamma is 0. So, bottom line is the following from this consideration, that we will have this linear dependence of X gamma on XP, and what we will have, therefore, the spheres, that should be sphere, so from different points. Which are inscribed in this cone, so that all these points form the line. And this you can see from this expression. It was X gamma, and this is X gamma over XP, and this is here is XP line. So that form line, which is given by that expression. And therefore, all these spheres will be inscribed inside the cone, because that will, you can imagine three-dimensional picture. And so what you will have is the cone. And then all these spheres emitted from different points will have such a configuration that they will touch the same line. So the phase at all these lines is the same, and therefore the phase of light along these lines is the same. Okay? Now suppose particle is produced here and is absorbed here, so it stops to emit light. So then this light will propagate further, and not what it will form. So that will be like this, and it will also be emitted in this direction. So it's not very symmetric. Okay, so that's like this. So it will be actual light which is emitted in, which will move in this direction, and then that forms the cone. So let me show you a smaller size so that you can better see the geometry. So if particle was produced and then absorbed at some point, what will happen? You will have this light. Moving in this cone. So you can imagine a three-dimensional picture. So you have this trajectory, and then the light will propagate inside these cones. So that if you have some wall here, which is formed by your detector, what you will see, and you put here photomultipliers, then you will see projection of this. So it's a smaller size, so you will see ring here, which is called Cherenkov ring. Now let us compute what is the direction of propagation of Cherenkov light. So what is this angle? So this side of this triangle is given by V gamma multiplied by TF. So here the light propagates more than from other points, right? So it's emitted in t equals 0. It propagates time TF, sorry, our time. And then this is velocity. Now this side is formed by the path which particle propagates. And therefore, this is V particle multiplied by TF. And therefore, cosine theta Cherenkov equals V gamma times TF over V particle times TF. And so it will be the ratio of two velocities. Actually, I put here V gamma, but this is, remember, this is our V phase. So, cosine theta Cherenkov equals V gamma over V particle. And of course it has sense when particle propagates faster than velocity of light. Otherwise you would have cosine bigger than 1. So we can write here also that this is V, which is given by 1 over n, and here is V particle. So here particle didn't lose any energy. Now suppose that particle propagates and loses energy on ionization or some other mechanism. Then what happens that this opening of the Cherenkov cone changes. So in the initial moment the cone was like this. Then particle loses energy. V becomes smaller, and so cosine approaches to 1. So you will have smaller angle, then even smaller, and then the angle just disappears, collapses. This is when particle loses the energy. And so V particle decreases. So let me reproduce the picture with these emitted spheres. If you have a velocity of light which is smaller than velocity of particle, then you will have the spheres which are in such a form. And they form the fronts which I have discussed. Now, if particle moves slower than velocity of light, then what you will have is the following. The spheres will be one inside another because particle moves slower. So that would be in the case where V particle is smaller than V phase. So the light propagates faster, right? Here you see what's going on. The particle propagates faster than light. And therefore, the sphere emitted in the next moment is shifted with respect to the original one. So the particle moves slower than light propagates faster. So light, which was emitted, for instance, from this point, it has this position of the sphere, but particle just moved this distance. And so the sphere emitted later will be inside the sphere which is emitted before. And therefore, no front is formed in this case. This is the case of the particle bigger than in phase. Now, Tam and Cherenkov, Cherenkov was experimentalist actually. The experiments were done by him and his supervisor Vavilov. So unfortunately Vavilov died and the Nobel Prize was given back to Cherenkov and also to Tam, who actually created the theory of, constructed the theory of this Cherenkov of light. In particular, he has found a spectrum energy spectrum or frequency spectrum of the light. Dn, number of gammas. And here I'm switching to quantum nature because, you know, in quantum theory and quantum mechanics, what we are doing, we first solve the wave problem, right? We solve the wave problem, we find these waves, how the waves are, and then we are giving interpretation of these waves. Interpretation as the amplitude of probability that the particle is sitting, for instance, in this point. Right? So, actually, what we have developed before, this is kind of classical wave picture, but then we go to quantum mechanics, and therefore we are giving this interpretation of these waves and this fronts as amplitudes of probabilities. So, which means that formation of such a front give us increased probability to find photons. And we can talk about the energies of photons or their frequency. So the number of photons emitted from a unit of distance and the interval of wavelengths lambda equals 2 pi charge squared. Well, this is clear. And then is factor 1 minus 1 v particle square, refractive index square, and then 1 over lambda gamma squared. So this is the energy spectrum of photons emitted. So actually what is staying here is this sine square theta Cherenkov. One should notice that refractive index depends on the wavelengths. So it changes, and therefore what happens if you depict the spectrum, this is lambda gamma, and here is dn over d lambda, it has the following form. It has such a decrease, which is due to this 1 over lambda square, but then there's a sharp cutoff of the spectrum, and in this point n lambda equals 1 over v particle. So when you go to lambda, to smaller and smaller lambda, or higher frequency, then n approaches 1, and therefore at some point this quantity becomes 0, or close to 0. And so, which means that here we do not satisfy condition that velocity of particle is bigger than velocity of light. And here there's a cutoff. So the spectrum has such a funny form. It increases to higher frequencies, and actually the maximum is somewhere close to blue light. And therefore you see the Cherenkov radiation usually as kind of blue light emitted by medium. So typically, dn over dx is 200 gammas per centimeter. I don't want to go into details of this in explanation, but just remember that the spectrum has such a form, very specific, and therefore you may immediately identify that if you see some light, that it is due to, this is produced by Cherenkov radiation. Now let me say a few words about applications. Again, let me draw this picture. You have, say, trajectory of the particle, and then it emits light. And if you have the wall with photomultipliers, then you will see the ring formed by this emitted light. So you will have ring. Very clear. I don't know. Maybe my drawing is not very precise. So the example, classical example, is a super Kamiokande detector in Japan. A detector which produced a lot of important physics results. It's a huge tank filled in by water, 50 kiloton of water, and on the walls they put photomultipliers which detect the light produced. And so what they see these Cherenkov rings on the walls of this detector. And they detect these rings. I will show you some plots. So what you can measure by detecting these rings, you can establish what is the length of trajectory of particle by just measuring this quantity, because that reflects this one. So this is the length of particle produced here and then absorbed here and produces this time. So of course, if particle has a long trajectory, you will have not a ring, but it will be just whole the area will be filled by the light, right? Okay, so this size of this, the width of this ring is related to the length of the trajectory. Of course, you can measure direction of the particle. You also can measure the energy of the particle. Which is reflected by intensity of the light. And not only this, you can actually measure or establish the nature of particle. And the point is the following. If electron propagates and emits Cherenkov light, usually it also suffers from multiple scattering. So the trajectory of electron is not just straight line in water, but it has such a scattering feature. And therefore, from different points of trajectory, it will emit the Cherenkov cones, which is kind of moving, right? And so as a result, you will see here kind of diffuse, no sharp rings. So you will have some diffuse rings. If you have heavier particle, like muon, which is 200 heavier than electron, then this scattering is not so important. So it has more straight track. And therefore, for muon, you would see these cones, these rings with very sharp borders. And they have very good identification using this criteria, if it is electron and muon. Questions? Yeah.
Shouldn't the spectra also depend on the nature of the medium? Because it's transitions of molecules.
Yeah, so it depends, of course, but you need to have this dielectric medium. This is what is important. And water is just excellent because you have strong deviation from one, and water is cheaper.
So
Of course, yeah, so that's why usually people are using this. However, in nowadays detectors, people combine different techniques. So they use scintillators. And then you can observe both scintillation light, which I've discussed, and also Cherenkov light. So you might have a combination. Yeah, so people are using different media, and therefore N is different, and therefore the cone size is different, and you can actually in this case measure different energy ranges because N depends on energy, on frequency. Yeah. Try also reproduce this simple geometry by yourself, because that's a really very simple thing. And if particle moves faster than velocity of light, then the spheres of the light emitted from different points of particle trajectory, they are not one inside another, but they are kind of shifted in such a way that touching line curve forms the line. Right? So all the spheres are sitting inside the cone. Yeah?
Is there something special happening? The same velocities are the same, the particle velocity and the light emitted of the medium, they are precisely the same velocity?
Say again. If the velocity of particle and velocity of light is the same,
yeah.
So then the cone degenerated will be just straight and then it will disappear. Remember, the cosine of theta is given by the ratio of two velocities. And if they are equal, then a cosine is 1, which means that theta is 0. So the angle of the emission becomes just straight and then disappears. The radiation disappears. Simply because in this case, you will not form this coherent fronts. So what you will then you will have emission of light, and the spheres will be one inside another. And actually, this is of course simplified picture. What will happen is that light from different points, emitted from different points, will also kind of interfere destructively, and you will not have such a thing. Okay? So, very briefly about particles in magnetic field. Magnetic fields are tools which we are using to manipulate with particles. So not only detect, but we can act on the particles and see what is the reaction, what is the feedback. And in this case, we can study properties of particles. So suppose you have magnetic field which is perpendicular to the blackboard, and you have particle and this field with momentum in a given point in this direction. So what will happen with this particle? The particle will move, and the particle is charged particle. It will move along the circular orbit, right? And the radius of this circle, which is Larmor radius, is given by, who remembers what is the radius?
E over QB.
What?
Momentum over Q. Charge
Momentum, yes.
over charge and magnetic.
And magnetic field, right. So that's more or less intuitively clear. You can, of course, immediately derive this using the equality of two forces. One is centrifugal, another one is produced by magnetic field, and equality of these two forces leads you to this formula. So of course, the bigger momentum of particle, the bigger radius will be, right? So a particle will not be bended strongly. And if B is bigger, and the bigger is B, the stronger particle is bended. So that's more or less clear. And the same is electra. So more or less this dependence is clear. What is less trivial that this radius doesn't depend on the mass of the particle. Actually, this is because both forces, centrifugal and produced by magnetic field, they do not depend on mass, and as a result, you will have this radius, which doesn't depend on mass, which is extremely important for our studies. So we can rewrite this formula as P equals E B multiplied by RB. Now what we can study? So we can impose magnetic field, and so we know this, right? This is known in our experiments. This we can measure. And so in this way we can find what is P and find momentum of the particle. Now, depending on the electric charge, of course we need to assume what is the charge of the particle. Because if it is double charge, triple charge, then correspondingly momentum becomes bigger. But in many cases we can guess what is the charge of the particle we deal with, and therefore, so we can find what is momentum. Now, depending on the charge, you will have curvature in two different directions, right? So you have magnetic field, and if in one case you will have motion in this direction, then in charge, for opposite charge, you will have this direction. Okay? So you can measure in this case momentum and the charge of the particle, so using magnetic field. So before moving to cosmic rays, let me finally summarize all our tools we are kind of possessing to study properties of the particles. So what we will in general consider are tracks of particles in magnetic field. So in many experiments we are managing to see the track of the particles. Also there are different methodics how we can visualize the track of the particle, and we will discuss this method. And we impose also magnetic field, and therefore what we can do is the following. We can measure the radius of particle, curvature of the particle in the magnetic field. That gives for us P, momentum, and charge of the particle, sign of the charge. we can measure to some extent thickness of the track, and that gives for us dE over dx, as we discussed before. In the case of ionization, that is proportional to z mx squared over momentum of the particle, and this is ionization. And in the case of radiation, it is proportional to z squared E over mx squared. This is ionization. So which means making assumption or kind of having some idea about which type of the energy loss occurs. And remember, we can see how the tracks changes along the way. So it changes differently. If you have ionization, tracks become more wider. In the case of radiation, it becomes thinner when particle propagates. And therefore, using these tools, we can measure P, electric charge, and the mass of the particle, right? Because using these formulas, and here we know what is Z, we know what is Z of our material. We measure P, and what we can determine the mass of the particle. And this is already enough to identify if we have some new particle. Remember, mass essentially is the very nice label for a given particle. So there is not many cases when you have degenerate masses, and we know these cases. So to measure electric charge and to measure the mass of the particle, we already know quite a lot. And many discoveries are based on precisely measuring these quantities. Questions? Okay. I will present some analysis of this type, how properties of particles have been identified and measured, established. So now we are going to discuss discoveries of particles in cosmic rays. It was a long epoch before accelerators overcome when new particles have been discovered in cosmic rays. So they were generated by cosmic rays. I mentioned already, interestingly, that we may come now again to the epoch when some new discoveries will be in cosmic rays. Or you will see what will happen. So, cosmic rays. Very briefly, also this is still very active area of research. The cosmic rays have been discovered in the beginning of last century, and Victor Hess got a Nobel Prize for discovery of cosmic rays. So, what was the first observation? The observation was spontaneous discharges of electroscopes. So, what are electroscopes? Probably you know this. So, two plates to sum the electric material, and then if you kind of rotate them and there's a friction, what you get the charges. So, these plates become charged. And so you can collect quite big charge on these plates. Now, what happens is, is that suddenly there are discharges. Of course, if you connect these plates by electron wire, then of course you will have a current. So that was used also to produce currents. But what happened is that in some cases you have spontaneous discharge. There's nothing kind of visible what can produce this. So that has been studied, and the question is, what is the origin of these discharges? Well, first what comes in mind, of course, there are some particles which ionize medium around electroscopes and between the plates. This ionization triggers discharges. So you have current and you have discharge. So appearance of ionization. Some external particles ionize medium, and then there are discharges. Well, the question is, what are these particles which produce discharges? So let me put here in this way. So particle, ionization, which then leads to discharge. So you will have appearance of free ions, and then they are moving and then producing the charges. So origin of the particles. And the first is there's some radiation around, especially that one expects some radiation from the Earth's crust. If so, then you would expect that if you put your device higher and higher, remove it from the surface of the Earth, then the frequency of discharges should decrease. Final point in this story was put by Victor Hess. In 1912, so quite recently we celebrated 100th anniversary of discovery of the cosmic rays, and he used balloons. So he was sitting in balloon, the balloon was flying up, and he registered the frequency of discharges of electroscopes. And what he has observed that the frequency increases when you go upper and upper. And the conclusion was that the particles which produce ionization in electroscopes actually are coming from above, from cosmic space. So particles have cosmic origins. That was discovery of cosmic rays. So let me summarize properties of cosmic rays very briefly again. So what we know about cosmic rays after 100 years of studies, and amazingly we still don't know what are really the sources of these cosmic rays. They're still not quite identified, but last year it was something which probably produced breakthrough in this understanding, and I will discuss this later. So, properties of cosmic rays. Actually, what we observe at the surface of the Earth are not primary cosmic rays, but these are secondary cosmic rays. Produced by primary ones, which interact with atmosphere. So this is atmosphere of the Earth. And they are interacting, primary cosmic rays, usually somewhere close to the upper layers of the atmosphere, let's say distances 20, 15 kilometers from the Earth. So, and those are protons, nuclei, electrons, also can be gammas. So they produce secondary radiation, which propagates, and this is what we are detecting close to the surface of the Earth. So what these particles produce depends on the nature of the particle. Electrons and gammas are producing electromagnetic cascades. Primary electrons produce electromagnetic cascades. So what is this? You have electron, which in the field of nuclei, as we discussed before, radiate, right? So electron, electron. In the field of nuclei, it produces gamma. I will not show here nuclei, but of course it's not. It cannot be in just vacuum, but in the presence of nuclear or electric fields, it produces gamma. Then it can do again this and again, so producing these gammas. Gammas, in turn, can produce electron-positron pairs. Again, not in vacuum, but in the presence of nuclei. And we show this usually by the diagram of this type. So gammas in the electric fields of nuclei can produce electron and positron pairs. And so what you will have here, cascades. And then secondary electrons also produce gammas, and then this cascade develops. If primary energy is very high, then the number of secondary particles can be huge. It can be millions of secondary particles produced by a single originally interacting electron. So these are electromagnetic cascades. Now, if primary cosmic ray is proton, and maybe even neutron, because at very high energies even neutron can travel big distances, or it can be produced by proton interacting with interstellar medium. So proton, which is more typical, and we expect that this is, it composes a big part of cosmic rays, at least at lower energies. Still open question what happens at higher energies. This proton also interacts with nuclei of atmosphere and producing secondary particles. And this proliferation is even faster because in a single vertex you can produce protons, antiprotons, and then particles which also have strong interactions, and we have not yet discussed this, and we will discuss discoveries. And among these particles are pions or K-mesons, all other mesons. Those particles in turn produce secondary particles, and we have this development of the cascades, which is called extended atmospheric showers. And the number of particles can reach hundreds of millions, so up to 10 to the 8 at the surface. And one of the detectors which measure this type of showers is Auger detector in Argentina, so probably we'll discuss it later. Now, total flux, just to have an idea, of secondary cosmic rays at energies bigger than 1 GeV is about 2 10 to the 2, 1 over meter square second, and then steradian. in average. Of course, you may be lucky or unlucky if, you know, this shower just hits you. I don't know, people haven't studied probably how this can affect the health. I mean, especially people who are, you know, going to mountains, and if you, of course the probability is not high that, you know, this huge shower will hit you. Maybe that actually, you know, it can damage, of course, the health. I haven't seen these studies. I thought maybe I should do this also. When completely retired, you know, to start to discuss this thing. Yeah?
I think they say that when you are up in the space, the rays make flashes on your retina.
Yeah, sure. You know, people just, of course, explored effects of particles on routinely, right? We have synchrotrons, we have proton beams studying this, but again, here you make a really huge amount of energy release. I mean, these showers are not so often of this type. Yeah, the energy is enormous, stored in these cosmic rays. Now, what is the spectrum? Yeah.
This is really that the summation of the energies of our particles have to be contained in the kinetic energy of the particle coming from the outer space,
Yeah.
or maybe when through this process in the atmosphere, it takes some energy from the atoms.
No, there is not much acceleration in atmosphere. So usually, what you have here in this secondary particles, they share by energy of original one.
And this energy could be
Or it's 10 to the 21 electron volts again. So this is the energy which is enough to take, say, 1 kilogram body and, you know, put it on 1 meter. Something we can imagine that. So what is this energy?
How can we not identify the source of these cosmic rays? Like they are just random events, or are they some more frequent periods that we can observe in a certain direction?
Well, you see, cosmic rays are charged particles, and they are traveling in magnetic fields. There are magnetic fields of the galaxy, of course, also in our solar system, but in galaxy, and even in intergalactic space. And therefore, charged cosmic rays like protons or nuclei cannot travel too long, too much. And so what we see is kind of isotropic spectrum. So there is no kind of very clear direction. And there is no kind of concentration in some direction or something like this. Of course, people try to identify some sources, let me come to this later because I want to first proceed. Proceed. But one thing which actually happens these days, for the first time, and that happened with this so-called ice cube event. So they have detected high energy neutrino, which can be associated with certain source, with active galactic nuclei. And for the first time, actually, neutrinos are traveling without any bending of the trajectory. So neutrinos are unique because they can travel really time comparable with the age of the universe, very remote sources. And so some progress now, you know, we might have kind of progress with this. So what is the spectrum, energy spectrum of cosmic rays? Well, low energy cosmic rays, the situation can be simpler. So we more or less understand they are produced in our galaxy, and they are accelerated in shock waves produced by explosion of supernova stars. So that for low energy, relatively low energies. The problem is for very high energies, they cannot be produced in our galaxy. It's just conditions are not enough to produce and to accelerate them. So that's a big problem. The energy spectrum has quite interesting shape. So dN over dE Sometimes people are multiplying by E squared, so to have it's flatter. Energy. And I will take above 1 GeV. So for kind of long energy, big energy interval, it's almost like a power spectrum with power minus 2.7. Then at the energy around 10 to the 15 electron volts, and I will measure this in electron volts, that is what we call knee of the spectrum. So, this power becomes bigger. Then at energy is around 10 to the 18. So maybe I should change the slopes everywhere. So it's like this. Then it's sharper. And 10 to the 18 electron volt, there's another feature, what we call ankle. So this is like a leg, right? So that's ankle. And then at around 5, 10 to the 19, we have a cutoff. So this is the shape of the spectrum. And the interpretation is like this. These lower energies, relatively low energies, these have galactic source. Produced in our galaxies, and as I said, Fermi actually a long time ago suggested a mechanism of acceleration when you have shock waves and particles are accelerated by shock waves. And now it's an upgraded mechanism, but the idea is that in shock waves you have, which contain magnetic fields, and then charged particles are accelerated.
This is in interstellar space, right?
Huh?
This is in the empty space.
Well, it's not completely empty space because these are in shock waves. Still, there are some densities.
So a particle moves into some kind of galactic dust or something, which produces...
No. So you have explosion of stars. So you have collapses, gravitational collapses of the stars. So what happens is the star, massive star, collapses, and then medium start to fall down, and there's a recoil, and so you have, when you see explosion, this is nothing but about expanding envelope, very hot envelope. So, and so you form shock waves, so that's kind of in the form of shock waves. And then shock waves also contain magnetic field. And when particle crosses these shock waves, it gets some energy, it gets enhanced. So that's a mechanism. And for these low energy mechanisms, it looks like it works, and more or less we can explain what's going on here. Now at these energies, what happens is leakage of cosmic rays from our galaxy. For low energies, and we know what are magnetic fields in the galaxy, these cosmic rays just trapped, so they kind of are reflected, and so they are traveling inside and live long time inside the galaxy. For higher enough energies, more radius becomes bigger than the size of the galaxy, and therefore those cosmic rays can go out. And this sharpening, which means the flux start to decrease faster, is most probably related to the leakage of the cosmic rays from our galaxy. Here, this ankle can be interpreted that what we have is the following. So these are galactic, and here we meet already flux coming out from outside of our galaxy, extragalactic source. So here's the flux of extragalactic sources. So it's not quite clear because the shape here is a bit more complicated, and it also it depends on what you assume about the chemical composition of cosmic rays. So where precisely you have here a change of galactic to intergalactic or extragalactic sources, it's not quite clear, but somewhere in this region it looks like you have already dominance of extragalactic. And then actually in our galaxy, we cannot produce too high energy cosmic rays because we know what are the sizes of the magnetic field, what is the size. So you essentially need to have accelerator, right? And to accelerate particles to very high energies, you need to have big enough magnetic field and the size of your detector. So LHC is 27 kilometers in circumference. So this is not accidental, because if you want to accelerate to higher energies, you need to have big radius of acceleration. Right? So the galaxy cannot produce cosmic rays in this range. Now, final is this cutoff, which sometimes people are calling GZK cutoff. Grazing zацепен Kuzmin. So what this gentleman recognizes the following. You have microwave background radiation in the universe, which is left over from Big Bang. And we know this radiation is 2.7 Kelvin, and actually we'll have exercise to estimate this energy. So what's going on? The cosmic rays traveling in this cosmic microwave background radiation at some point start to have inelastic collisions. So they start to produce secondary particles after some threshold, after some energy, below not, but after some energy they start to produce pions and other things. And they lose energy, and therefore they cannot travel from very long distances. So that's something like 30 megaparsec. I don't know if you know what it is, parsec or megaparsec. So maybe 30 megaparsec. And therefore, you can collect at your place just cosmic rays from the sources which are not too far. And because of this reason, you have this cutoff. Well, there is still another interpretation, is that if cosmic rays dominantly are iron, not just protons, and this has some sense because in the explosions of supernovas, so explosions occur when the core is mostly made of iron, and therefore it may happen that a substantial contribution comes just from iron nuclei. Another interpretation of this cutoff is just, again, on this microwave background radiation, iron nuclei are just split. And therefore, the parts of original nuclei will have lower energies. So we need to have more events here in this range to distinguish these two mechanisms. Still, it's open question. And actually here also, this what Auger experiment is telling us, it's not clear. It looks like we have a change of chemical composition with increase of energy in this range. And it looks like contribution of ions become bigger with energy. So this is not yet settled down. So what are these active galactic nuclei? So these are essentially extremely massive black holes and some objects of galactic scale, and the black holes with the masses 10 to the 6 of solar masses or even bigger. And so what happens is this black hole, and there's material around, and there's accretion of material onto the black hole, and some engine exists which is not very clear that the energy, when you have this motion of the matter on the black hole, is emitted into jets, which are, so you have accretion disk usually, so the body is rotating, black hole inside, so you have this disk, accretion occurs, and jets of matter actually are emitted into opposite directions. And we see this clearly, these jets in pictures Yeah.
Those are the methods that do not have the chance to enter to black hole, but somehow.
No, it enters. Part of this enters, but part is emitted in this.
But there is nothing emitted from inside of the black hole.
No, that's something which happens. Something happens. Some engine happens, around the black holes. Not. So which means, of course, you have very strong magnetic fields, rotation, and that kind of boil into these jets, which are even ultra relativistic. It's amazing that matter, in a huge amount of matter moves with this relativistic velocity, it's close to the velocity of light. And the story is the same. It is supposed that there are magnetic fields and shock waves in these already jets, and then acceleration of cosmic rays up to this high energies occurs when these shock waves propagating inside these jets. So the first neutrino was detected by IceCube last year, which is associated with such a type of the object. So we need to have, of course, more information. Well, maybe, please ask me the questions. I want just to probably to say, finally not, that I will start this next lecture. Yeah. Question? Well, this is interesting topic. I think that maybe some of you will work on this cosmic rays, cosmic neutrino stuff. There's some of the area which is really produces new and interesting results. And I told already there's this IceCube detector in Antarctica, inside the ice, and new detectors are kind of planned to be constructed. One is the underwater, huge underwater detector to detect neutrinos of these high energies. And also there are new detectors for cosmic rays, and so this is quite interesting. May have not only astrophysical implications, but also something for particle physics. And of course, this first detection of gravitational waves from sources like mergers, and in particular merging of neutron stars. That's kind of interesting. It may shed also light on this high energy phenomena and generation of cosmic rays. So this is what we call multi-messenger astronomy. This is what it is when you detect gammas, you detect cosmic rays, and now neutrinos, and you can actually get important information out of this. Yeah.
Consider the electrically neutral cosmic rays, like very high energetic gamma rays, or the neutrinos, or maybe neutrons.
No, mostly these are protons and nuclei. Now, neutrinos here, we are probably have something like 100 neutrinos detected by IceCube. Now, neutrons, again, what I was telling, so neutron is decaying particle. Gammas, again, cannot travel too far, high energy gammas, because they are also interact with cosmic microwave background radiation, producing a plus or minus pair. So there's a cascade even in the universe.
In the empty space.
No, there's no empty space. You have this microwave background radiation, which is not a joke. So they are everywhere, and the gammas are produced maybe of high energies, but then the energy decreases, so they cascade and move everything to lower energies. Actually, this is an important thing, because we think that neutrinos are produced in the case of pi plus or pi minus, and simultaneously pi zeros are produced, and pi zeros are giving the pair of gammas. But we do not see these gammas. We can still see these neutrinos, and probably we are detecting these neutrinos from pi, most probably. So these are neutrinos from pi and decay. However, gammas of these energies cannot reach us, and so everything is kind of moving to lower energies, and then the detector like Fermi, it detects lower energy gamma radiation. But still there is some connection because of the energy, and when they have this cascading more or less conserves, and so you now should worry, and now big discussion is consideration that if you invent some model, you need to satisfy bounds from Fermi and outproduce. So there's a connection also between these two.
But there is not enough detectors on Earth to make a survey with all possible neutrino detections over the sky.
Well, what do you mean all possible? So in Antarctica they see this. We have not enough money. Otherwise, we would produce bigger detectors, many detectors. So there's only one actually acting. This is at least underground, underworld, under ice detector. Now they see neutrinos in principle from everywhere. However, at very high energies, Earth becomes already opaque for neutrinos. So mostly for high energy neutrinos, they see only from particles which come from the south. Yeah, so there's idea also to have these big detectors in the north, and one will be probably in Baikal Lake in Russia, and another one is in Mediterranean, near Italy and also Greece. Okay. Okay, so then see you on Monday, and you please bring your solutions, and on Wednesday you will have the checks of your exercises, and our postdoc Takeshi Kobayashi will deal with you with your solutions. Okay.
What time will it be?
I think it should be on schedule already. It will be Wednesday.
There is no tutorials on this course on schedule.
Oh, okay. So then I should. It will be on Wednesday. I think the same time as a lecture.
Okay.
But I will confirm on Monday. Certainly it will be on Wednesday. So this is just free day when we have no lectures. And on Monday I will give you a new set of the second one. So you will have every Wednesday check of all the solutions. Okay.